Hello, my friends. I am so sorry that my Zoom client just keeps crashing and dropping out. I am reaching out and working with the IT department to figure that out so it stops happening. I really want to thank you for your patience and just being willing to be flexible with this whole situation. So let's get started and revisit today's lesson on periodic trends. Welcome to the periodic table. Specifically, we'll be talking about the periodic trends today. And since we started our discussion on the periodic trends last class, this is going to be our part 2. So first, an outline of what's going to be covered in this lesson. So we're going to review the basic organization of the periodic table, which you may see me abbreviate sometimes as PT. We will go over the definition of ions and how they tie into periodic trends. Then we'll discuss the 3 major periodic trends, which include atomic radius, ionization energy, and electron affinity. Again, here is a link to a periodic table if you would like to follow along with your own version of it. So organizing the periodic table, we have groups versus periods. Now, when the scientists who developed the modern periodic table were putting it together, they decided to give the rows and columns very specific names. So our vertical columns are called groups, and our horizontal rows are called periods. And the groups actually have similar properties. So this first column of the alkali metals, these have similar properties. The second group of our alkaline earth metals, these have similar properties. So the vertical columns are the ones that have the similar properties. Periods, not so much. So again, groups have similar physical and chemical properties. And last time we talked about these various groups and also blocks and chunks on the periodic table. And so for these various groups, I have highlighted the alkali metals, alkaline earth metals, transition metals here in the center, halogens, and then noble gases. I'm expecting you to know where those groups are on the periodic table. So that if I say, hey, look at chlorine, it's a halogen, you'll know to look at the right side of the periodic table in that second to last column. So please know where these various groups and blocks are on the periodic table. All right, next up, periodic trends. Specifically, we will be discussing here, why do we care? Why do we care about these trends? And really, it's because they help explain a lot of the group properties, so those columns of properties. So for example, why do the alkali metals of group 1, lithium, sodium, potassium, react so violently when they contact water? If you remember, they are pretty soft, silvery metals. You can actually just cut it with a knife, which is crazy. But then when they come into contact with water, just plain old water, why do they combust? Why do they react so violently? That's what periodic trends can explain. Additionally, for example, let's look at the halogens. The halogens, far right side of the periodic table, non-metals. But why do they react so strongly with so many things? So chlorine tablets, for example, I mean, those kill microorganisms in your pool. Like, that's pretty extreme. Or maybe, if you've had blood drawn or surgery or like ears pierced, you might have gotten iodine, shown here on the right, that weird yellowy color. You might have gotten that as the word I'm looking for, like antimicrobial, antiseptic. There we go. I got there. So like, why are these elements, like, how can they do this? Like, why are they so reactive? And the periodic trends help us explain these properties. And so not only do they help us explain, but they help us predict, right? So if you had a chunk of sodium on you, just a chunk of sodium, and you knew that lithium reacted that violently with water, well, you could predict that maybe your chunk of sodium would react that way too. So the three specific periodic trends we will be discussing include atomic radius, ionization energy, and electron affinity. Next up, we will be discussing the periodic trend of atomic radius. So atomic radius, I feel like this word is kind of self-explanatory. It is literally how wide is an atom, how big is an atom. And up until this point, we have been discussing atoms, and we've been talking about them like they're all the same size, but they're actually not. So the size depends on the number of electrons and also which orbital is the outermost orbital, which energy layer, energy shell is the last one. So imagine that an atom is like a magnet. So we have the positive nucleus, and it's attracting the electrons, that negative charge on the outside. We know that opposites attract, right? If you have two magnets, opposite poles, they attract positive, negative. But the same charges repel each other. So those electrons are floating on the outside. They're social distancing because they repel each other, right? Negative charges repel each other. But that nucleus, that positive nucleus, it's attracted to those electrons. So they're trying to grab, those protons are trying to grab those electrons and hold them really, really tight to the nucleus. But let's add another layer to that. So you can imagine that the orbitals nest inside of each other like Russian nesting dolls. So we have layer 1, layer 2, layer 3, layer 4, and so on. And I'm going to show y'all a really corny demo with illustrating orbitals and the electrons. Pretend that I am a neutral atom, just an atom, and I need to go grab my electrons. But I can only carry 2 electrons per pocket. My electrons will be represented by these marbles. So let's start. Because I'm wearing women's clothes, my pants only have 2 pockets. So I can put 2 marbles in one pocket, 2 marbles in another pocket. All right. If I want to add any more electrons, I'm going to have to add another layer, another energy level of orbitals, right? So, all right, so I have my lab coat on over my regular clothes, and this lab coat has 2 front pockets, 1 upper pocket, so 3 pockets total. That means I can fit a total of 6 electrons into this layer, right? So let's do that. 1, 2, 3, 4, 5, 6. There we go. All right. So if I want to add even more electrons, I'm going to have to add another layer. Okay, I got another layer on. So I have more pockets, so I can fit even more electrons into these pockets. Whew. What I hope you're noticing is that as I add on more layers, as I added on the lab coat and my big winter coat, I'm getting bigger, right? So for elements, for atoms, as you add on more layers of orbitals, it's going to get bigger and bigger. So as we go down a group, right, as we are jumping in energy levels down that column, we're going to get bigger, bigger, bigger. Overall, the atomic radius, or the size, decreases from left to right across a period and increases down a group. So we can see that these elements here are represented by these little green spheres. And the top right is very, very tiny, and the bottom left is pretty big. So here is another representation in which it is, the arrows are showing us increasing atomic radius. So it gets larger as we go to the left and down. Now, it might help some of y'all to remember this if you think of the thick elements being in the bottom left corner and the stick elements being in the top right corner. Next up, we're going to discuss what is an ion and why does it matter? Why is it important for the periodic trends? This slide has a lot of words on it, but they are very important words. First off, an ion is an atom with unequal numbers of protons and electrons. So far, we have been talking about elements and atoms like they are all always neutral. But that is actually not the case. Not all atoms are neutral. Not all of them are always neutral. A lot of them are actually charged positively or negatively most of the time. So neutral means that we have equal numbers of protons and electrons. No overall charge. But atoms can sometimes gain or lose electrons. We are specifically talking about electrons here, y'all. Electrons are gained or lost. Remember that the protons and neutrons live happily in the nucleus, and we are not going to touch the protons. The electrons are what we take away or give. Atoms with unequal numbers of protons and electrons are called ions. Here is a picture schematic. So we have a neutral atom in the center, and if we lose electrons, right? If we lose electrons, lose a negative charge, we become overall positive. So lose electrons, become more positive. This type of ion, a positively charged ion, is called a cation. Now, y'all know from the South, and a bunch of people in the South, when we first learn this word, we say it as cation, which is not right. It's not like cashew, it's cation, like a cat, like the animal. A neutral atom could also gain electrons. So when it gains an extra negative charge, it becomes overall negative. And now it is an anion. So anion, that's how you pronounce it. This is overall negatively charged. Notice that I made these two, the cation and the anion, different sizes. That is on purpose. Cations are generally smaller than the neutral atom. Anions are generally larger than the neutral atom. So cations are generally smaller because if we pick off an electron from the outer regions, right, that nucleus, those protons, are going to try to grab those remaining electrons and just really, really hold them tight, really hug them tight. They don't want to give up even more electrons. They're going to hug those remaining electrons really, really tight, and it's actually going to get smaller. The atom's going to get slightly smaller. The way I remember this is that I always think of cats as pretty small, at least compared to dogs. So cations get smaller. All right, anions are generally larger because, y'all, if we add electrons to other electrons, that's a lot of negative charges just floating around. They're going to repel each other. They're going to try to socially distance. They're going to try to spread out, socially distance. And when they spread out, they make the atom bigger. So they repel each other, they socially distance, and the anion is bigger. I want to point out that certain elements are more likely to become cations or anions. That not all elements on the periodic table will want to be cations and anions. They will have a tendency to form one over the other, a more positive charge where they lose electrons, or a more negative charge where they gain electrons. And then to add to that, it takes different amounts of energy to give or take electrons to certain elements. So if it takes a ton of energy to add an additional electron, that element probably isn't going to like that. But if the element is just super happy to gain an electron, it just really wants another electron, y'all, it's probably going to gain that electron and form an anion. So we explain these trends through these periodic trends. Specifically, we're going to talk about ionization energy and electron affinity. But first, I want to ask you a very important question. When an atom ionizes, so when it either loses electrons or gains electrons, why does it not turn into a different element? Why is it that when sodium loses an electron and becomes sodium plus, why does it not turn to another other element? I really earnestly want you to ponder this for a second. What determines an element? What makes elements different from each other? Remember that the number of protons determines the element. And we're not touching the protons here. We're just changing the electrons. So that's why it doesn't turn into a different element. That would be alchemy. That would be really cool, but that's not what happens. We are just basically messing around with the electrons. Okay, let's dive into ionization energy. Ionization energy is how much energy is required to take an electron away from an atom. So ionization energy specifically refers to removing an electron, not gaining, removing. And you'll see that it's measured in a specific unit called the joule, or capital J. It's just a unit of energy. Just like how calories on our food are energy, joule is also a unit of energy. And I want to actually revisit that really corny example of the jackets and the marbles. We are back to our example where I am an atom and I have multiple layers on, right? Multiple orbitals. And I also have a lot of electrons in each orbital, a lot of marbles. So I want you to consider, if you were this atom, how would you go about removing an electron? What layer, what orbital would you start with? Would you start closest towards you? Would you start farthest away? Well, the easiest way is to take from the outermost layer. So my outermost layer here is my winter coat. I'm going to reach into my pocket, pull out an electron, right? So it's a lot easier to do than reaching towards an inner layer. So we're going to work our way outside inward for removing electrons. It is easier to remove an outside electron than an inside electron. Consider why it makes sense that we would remove the outermost electron first. In terms of magnets, you probably have a fridge at home, probably in your kitchen. So let's consider that fridge. On that fridge, you might have some magnets, right? I'm going to draw them as little triangles. So you have some magnets. If you are all the way across your house, with a magnet in your hand, just a plain old magnet. Is the fridge magnet and the magnet in your hand, are they super attracted to each other? Do you feel the connection between the two when you're between walls, maybe up or down the stairs? No, there's a distance dependence, right? If you were to go very close to the fridge and get the magnets to really interact with each other, to almost touch, then you would feel that connection, that strong pull between them, right? Consider that the fridge is our nucleus of our atom. And consider that you, with your magnet, well, you are the electron off in the cloud. So electrons that are more tightly knit, more tightly pulled to the nucleus, it's going to be harder to pull those electrons off. But if the electrons are farther away from the nucleus, they are the outer layers, the outer edges, it's going to be a whole lot easier for us to pick those electrons off. Now, let me redraw this to look more like an atom. Here is a picture of a Bohr representation of our atom. Remember, the Bohr one has these concentric rings. So our nucleus is in the center, and it has an overall positive charge. And so any of these electrons that are in one of the inner orbitals, so really around here, for example, these are going to be tightly drawn to those positive charges. But we can see we have electrons floating on the outer edges, and so these ones are going to be a lot easier to take away. The nucleus is not pulling as hard on these far reaches. So that is why bigger atoms have a smaller or a lower ionization energy. It takes a lot less energy to pick off those very outer atoms. If an atom is small and tightly bound, it's going to be a lot harder to pull these electrons away. Again, we take the outermost electron first. Just like you layer up, on a cold winter day, you got to take off that outer layer first. You can't just start with the inner layer. Or going back to our nesting doll example, right? We got to take off the outer layer before we can get to the inner layer. And perfect time for a Shrek joke. Onions have layers, but this actually does work with this for an example. So the farther out the electron, the less energy it takes to remove it. My question to you is, the bigger or smaller the atomic radius, the less energy it takes to remove an electron. So I just told you that the farther out the electron is, the less energy it takes. So is that a bigger or smaller atomic radius? Hope you said bigger, right? Because then it's spread out. So the bigger the atomic radius, the less energy it takes to remove an electron. So again, looking at that atomic radius chart, ooh, look, we can start connecting the ideas. So the big elements down here, like Fr is francium, these are easier to take electrons from. The top right, they do not want to let go of their electrons. You are going to have to put in a lot of energy to take any of their electrons. So thinking in terms of ionization energy, like labeling it on the table, right? So the ionization energy increases as we go left to right and upward. So top right corner, high ionization energy. Again, these elements don't want to give up their electrons. So they're going to hold on as tightly as they can. And it takes a lot of energy to take away an electron. So now that we have considered how an atom can ionize, how it can add or remove an electron, let's actually write this as a chemical equation. And I know that this is one of the first times we are really exploring like how to write a chemical equation, but this is really a good segue into it. So how do we write out the ionization of an atom? Let's understand how to write a chemical equation in general first. Chemical equations involve reactants and products. These are these specific terms that we use in science, in chemistry, for chemical reactions. In more layman's terms, this is the stuff we start with and the stuff we end with. And in chemistry, we like to get pretty specific with this stuff. We don't like to just, pretend something vanished. No, we want to account for everything that's going on. That's what makes it chemistry. So the stuff we start with are the reactants. Stuff we end with are the products. I want to point out that sometimes it's not always plural. It's not always multiple reactants, multiple products. Sometimes it's just one reactant, one product. Okay. So consider ionization energy. So ionization energy involves removing an electron. So our reactant here, our starting material, is a neutral atom. What do we end up with for products? There's actually two products here. Remember, we want to account for literally everything involved. So you take a neutral atom, you remove an electron. So what is the neutral atom that has lost an electron turn into? Is it more positively charged or negatively charged? So if we remove an electron, that neutral atom now becomes a cation, an overall positively charged, right? Positively charged atom. Ooh, but y'all, our other product is actually an electron. We don't just get to forget about this electron, right? We grab it, we pull it out, and it's there. Like, we don't get to just pretend the electron doesn't exist. It is one of our products. So one example of an element that easily gives up one electron is sodium. Sodium is Na, and this is our reactant. So we're going to put it on the left side, on our reactant side. Then we're going to have an arrow that represents chemical, like chemical equation is happening. And we have had some chemistry happen here. And our products here are Na plus an electron. And notice that I do give the little superscripts of plus and minus. So in this case, that little plus means +1 because we've lost one electron. If we lost 2 electrons, it would be a 2+. All right. We can also show this trend in a more of a 3D periodic table. And I like these actually a lot better than just like the color coding. I think this is easier to see, like, oh, look, the relative height is a lot different. So as we go towards the top right, we have very high ionization energies, right? Over on the left, these are lower, smaller, not as much ionization energy required. So if we think in terms of, does it gain electrons or lose electrons? Well, over here on the left, it doesn't take that much energy to pick off those electrons So they're more likely to lose an electron. But this area over on the right, they are more likely to gain an electron than actually lose it. And that's important because when we start noticing these trends, we can start figuring out how atoms would interact with each other. So, elements that lose electrons like to interact with elements that gain electrons, right? One can donate an electron to the other, and that's chemistry. For example, if we have table salt, Na plus, Cl minus, right? It has gained an electron here. They come together to form NaCl, a neutral compound, table salt. Next up, we have the periodic trend of electron affinity. Electron affinity is the energy involved in an atom gaining an electron. So if you have an affinity for something, you want it, right? Like I have an affinity for dogs. I like dogs. So electron affinity is when an atom wants another electron. Again, this is measured in joules, J, which is a type of a unit for energy. We discussed that certain elements will want to give off electrons and certain elements will want to take electrons. So you can imagine the elements that do not want another electron, they're already stuffed. They don't want more electrons. They're like an overstuffed suitcase where, oh, if you need to stick any other piece of clothing in there, another electron in there, ooh, it's going to take a lot of energy, and the atom is not going to like it, and it may not even be stable. So some elements do not want another electron, and you really have to put in a lot of work, a lot of energy to make it take an electron. Some elements are so eager to gain an electron, though, that they actually get so happy that they give off energy in the process. They're like, yes, let's do this. I want another electron. And they just whoop, they take it. And this always reminds me of Patrick. When it comes to food, he's just like, yes, yes, yes. Like, you don't have to ask him twice, right? Like, he's just like, yes, energy, or yes, food. So, words, y'all. Patrick is always happy to eat more. And this is like elements that want electrons. Okay. So, the smaller the atom, right, the closer everything is to the nucleus, the more it wants an electron. So, smaller wants electron. So, this chart, increasing electron affinity. So, increasingly want another electron. We see that's a lot of this top right here. Ooh, notice our patterns. Notice our patterns between size and electron affinity, size, and ionization energy. So again, on the left, we are more likely to lose electrons here. This is like the overstuffed suitcase. And on the right here, we are much more likely to gain an electron, very happily too. So let us talk about how to write the chemical equation for electron affinity. Again, we start with the stuff. We start with our reactants, the stuff we start with, and then we end with our products, the stuff we end with. And then we always use this arrow to indicate that a chemical reaction is occurring. So, electron affinity involves gaining an electron. So our products are an anion. This is an atom with an overall negative charge. So it has eaten the electron and is now overall negative. So what two things did we start with? What two things come together to make an anion? We had our neutral atom that we started with. We also have an electron. We can't just forget that. We can't just pretend the electron doesn't matter in our chemical equation. We are talking like chemists, we are thinking like chemists, and so we have to include that electron. It is important. An example of an atom gaining an electron is chlorine, Cl. This is in our halogen group. So chlorine is super duper happy to get another electron. It actually is so happy that it gives off energy. We don't have to put any energy into this process. It's just like, ooh, let me take it. So our reactants here are neutral chlorine plus electron, yields, a lot of this time this arrow we read it as yields, Cl minus. And again, notice I put that minus sign to indicate that it is negatively charged. So again, we can also show this trend of electron affinity with a 3D table. Again, I think this is a lot easier to visually interpret. So all these elements, top right, they want more electrons. They really want more electrons. So again, left side, more likely to lose electrons. Right side, more likely to gain electrons. And we're going to go over this next class, but what group sticks out to you in this graph? Like, what group? So column, right, group. What group do you notice? Maybe doesn't fit in with the trend. Ponder it. We're going to come back to this. Oh, well, I kind of gave it to you, but actually, so I did kind of give it to you in the slides, but why? I want you to consider why. So the noble gases, so this right-hand column, don't fit in our trend. They really don't want another electron. They're pretty unreactive. Why? Why do you think? So the periodic trends are all based on electrons. Y'all, everything's coming back to electrons. They are super duper important. Yeah, I don't really know how else to explain, like, the importance. Electrons are very important. Without them, we wouldn't have life or electronics. So that is the end of this lesson. So next time, we're going to link electron configurations to periodic trends. Please complete the homework by our next class period. Bye, y'all.